So today I will be speaking on Monsky's theorem. So this talk is organized by Curry Leaf, and this is a math club of MTTS alumni. So let me go ahead with the theorem. So Monsky's theorem, the statement says that we cannot divide a square into an odd number of triangles having equal area. So before I go ahead with the proof, I invite you to check for yourself that we can always divide a square into an even number of triangles having equal area, and any even number of triangles is possible. So in this lecture, we will make an additional hypothesis that the vertices of the triangles have rational coordinates. We will see why this is needed. So for proving this theorem, if we prove it for a particular square, then it is same as proving for any square. So we will prove the theorem for the unit square, and if we divide the unit square into triangles which have equal area, then the number of triangles has to be even. So the unit square is the square whose vertices are E1, E2, the origin, and E1 plus E2. So the theorem 1 will follow from another theorem, which we call theorem 2. And this says that if we divide the unit square into triangles, then there is at least one triangle such that the two-adic norm of its area is greater than 1. Now, I will describe what is the two-adic norm in the next slide. But before that, let us just notice that in theorem 2, we are not demanding that the triangles have equal area. Okay? We are just saying you divide anyhow into triangles in any way, then there will be at least one triangle with this property. So let us see what is the two-adic norm first. So the two-adic norm is defined for rational numbers. So if I have a rational number in the form m by n, where m is in Z, n is a natural number, and the GCD is 1. So if the rational number is non-zero, then we can write it uniquely as some power of 2 into another rational number, where this power of 2 is an integer, and both the numerator and denominator of b are odd. So here's an example. If I have 15 by 14, then I can write it as 2 power minus 1 into 15 by 7. And this is in a unique way, we can do this. So we define the two-adic norm of A to be 1 over this power of 2. So for example, here for 15 by 14, the two-adic norm will be 2. So what is the intuitive idea? That the more a number is divisible by 2, for example, if I take 2 power 10, then the two-adic norm will be 1 over 2 power 10. So the norm becomes smaller. Okay? And if the denominator is divisible by a large power of 2, then the norm is big. And for 0, we define the two-adic norm to be 0. So this is a norm on Q. So why we are calling it a norm is because it satisfies the properties of a norm, which are, so you are all familiar with the absolute value, which is also a norm on rational numbers. So the two-adic norm is always non-negative, and it is 0 only if A is 0. the two-adic norm of a product is the product of the two-adic norms, and the two-adic norm of a sum is less than equal to the sum of the two-adic norms. So these three properties are satisfied by the usual absolute value of a rational number, and any function which satisfies these properties is called a norm. So that's the reason for the name. And here 2 is playing an important part, so it's called the two-adic norm. Now this third property is actually following from a stronger property. Okay, so it is that if the two-adic norm of A is greater or equal to two-adic norm of B, then the two-adic norm of the sum is at most the two-adic norm of A. Okay, so and from this you can see that because two-adic norm of B is greater or equal to 0, so we will get this property. This is called the triangle inequality. So it follows from this property, because one of them has to be bigger than the other. But now we have another fact that if it is strictly bigger, one of them is strictly bigger, then it is the two-adic norm of the sum is equal to the bigger one. So we will be using both these facts as well as the multiplicative property. Okay. So these three facts will be used by in what we do next. Now let us see how theorem 2 will imply theorem 1, or in other words, how theorem 1 will follow from theorem 2. So recall that theorem 2 was saying if we divide the unit square into triangles in any manner, then there is at least one triangle whose area has two-adic norm strictly bigger than 1. Now from this theorem, we wanted to prove theorem 1, which was saying if we divide the unit square into triangles which have equal area, then the number of triangles has to be even. So let us see how theorem 1 follows. So we are assuming theorem 2 now. So if we divide the unit square into k triangles and all the triangles have the same area A, so we want to show k is even, right? So now because the total area of the unit square is 1, so I have k times A is 1. And now taking the two-adic norm, so since the two-adic norm of 1 is 1, we'll get two-adic norm of k into two-adic norm of A is 1. Now theorem 2 is telling us that there is at least one triangle whose area satisfies this property. But here all the triangles have the same area A. So I can say that two-adic norm of A is greater than 1. And because of the product of these two is 1, so two-adic norm of k has to be strictly less than 1. Now k is a natural number, right? We are dividing into k triangles. So if I have a natural number, if it is odd, then the two-adic norm will be 1, because there is no power of 2 which is dividing it. And if it is even, then the two-adic norm is 1 over a power of 2, a positive power of 2. So we see that the two-adic norm is less than 1, and therefore k has to be even. It cannot be odd. Okay, so we have seen that theorem 2 will imply theorem 1. So now we will focus on theorem 2. Okay. So in theorem 2, what we see is that we have to somehow show that the area of a triangle has this property. So to do this, we will use a coloring of the rational points, points having rational coordinates. So how do we color? So if I have a point in Q2 then I look at the tuple x comma y comma 1 and I look at the two-adic norm of these numbers, okay? And the first maximum where it occurs, based on that, based on the position of that first maximum, we will color the point x comma y. So let me explain that. So for example, if the first maximum is at x, what does it mean? That the two-adic norm of x is greater equal to two-adic norm of y, and also two-adic norm of x is greater equal to two-adic norm of 1, which is 1. In this case, we color it red. Okay? We color xy as red. And we color it green. So when I say we color it, it is just a short form, okay, of saying this property, that the first or the property in the brackets. Okay, so saying that x comma y is red is same as saying the coordinates x and y satisfy this property. Okay, so it is just instead of saying this long thing, we just say it is red. Same way, we say it is green if the coordinates satisfy this. The first maximum is at y. So mod y is strictly greater than the two-adic norm of x and also greater equal to 1. And blue, if the first maximum is at 1, so two-adic norm of x and y both are strictly less than 1. So for example, if we have these vertices of the unit square, they get these colors. So let us just check for the origin. So the origin we are saying should be colored blue, and that is because the two-adic norm of 0 is 0. So this condition is satisfied, and so it gets the color blue. You can check similarly for the other vertices. A triangle whose vertices are having rational coordinates, we will call it a rainbow triangle, or so the vertices should have different colors. That means it should be a red, green, and blue triangle. Okay. Now, why is this interesting for us? And in fact, why we are defining this coloring is because of this property that the area of any rainbow triangle satisfies this property, that the two-adic norm is strictly bigger than 1. Recall that in theorem 2, we wanted to prove that there is a triangle with this property. So let us prove this. How do we prove this, that any rainbow triangle has this property? So first we will prove it when one of the vertices is the origin in a special case. So that's why I will call it theorem 3 prime. And we have already seen the origin gets the color blue. So in this case, when the blue vertex is the origin, let us see a proof that the area of a rainbow triangle has to be strictly, two-adic norm should be greater than 1. So suppose I have a triangle with vertices u, v, w, getting red, green, and blue colors. Then let us give these names A, B, C, D, and the origin. Now, if a triangle has area A, then 2 times the area of the triangle is same as the area of the parallelogram, which is spanned by U and V. Okay, and the area of the parallelogram spanned by U and V in R3, we can take the norm of the cross product of these two vectors will give us the area of the parallelogram, and that norm is just mod of AD minus BC. Now we are assuming U is red, that means this condition is true. and V is green, that means this condition is true. So from both these properties, we can see that two-adic norm of AD is strictly bigger than two-adic norm of CD using these two. And using these two, we can see two-adic norm of AD is greater equal to 1. Now, how will that help us? Recall that the two-adic norm of a sum, okay, if one of them has strictly bigger norm, then it is equal to the bigger one. So we can conclude that the two-adic norm of 2A, which is the two-adic norm of AD minus BC, here the modulus doesn't matter because the two-adic norm is the same for whether it is x or minus x. They both have the same two-adic norm. So the two-adic norm of AD minus BC is just the two-adic norm of AD, which we have greater equal to 1. And therefore, we can say that the two-adic norm of A is greater equal to 2. Why is that? Because the two-adic norm of 2 is half. So I can say that I take 2 on this side, I get this, and therefore two-adic norm of A is strictly bigger than 1, which is what we want to show. So we have proved theorem 3 in this special case when one vertex is at the origin. Now, let us see what we mean by this invariance under translation by blue points. What we mean is that if we have points red, green, and blue colored, then the red point minus the blue point will be colored red. The green point minus the blue point will be colored green. So this is what we mean by invariance under translation by blue points. Okay, so this lemma will help us to prove theorem 3 in the general case. So let us just see a proof of this. So if the points are A, B, C, D, and E, F, then U minus W is A minus E, B minus F. Now U is red, that means this property is true for the coordinates of U. And W is blue, that means the coordinates of W satisfy this property. To show that U minus W is red, we have to show that the coordinates of U minus W satisfy the property of being a red point. That means these two properties should be true. Now, we are just using what we have. So, okay, we are given these two conditions. So from these two conditions, you are able to prove this and well, you are able to prove this, okay, because two-adic norm of A is greater equal to 1 and 1 is greater than two-adic norm of E. So the difference will be the two-adic norm of the bigger one, and that we know is greater equal to 1. So we have proved this part, okay. Two-adic norm of A minus E is greater equal to 1. How about the first part? So the first part, we will make two cases. So the case 1 is when two-adic norm of B is greater equal to two-adic norm of F. In that case, I know the difference will be having two-adic norm less than equal to the bigger one. Now in this case, what we want to show that this quantity is less than equal to two-adic norm of A minus C. So two-adic norm of B I know is less than two-adic norm of A. And from this, what we have already seen in this line, two-adic norm of A is two-adic norm of A minus C. So we have proved in this case. The other case is when we have proved this inequality. The other case is when it is strictly less. In that case, the difference has norm equal to the bigger one. And now the two-adic norm of F is less than 1. 1 is less than, the two-adic norm of A. Again, two-adic norm of A is equal to the two-adic norm of A minus C from this. So in both cases, we have shown that two-adic norm of B minus F is less than equal to two-adic norm of A minus C. That means the coordinates of U minus W satisfy the condition to be a red point. Okay, so similarly, we can show that the coordinates of V minus W satisfy the conditions to be a green point. Okay, same arguments. So I will not write that. Now, how will this lemma help us to prove that? Recall, we want to show the area of a rainbow triangle is having two-adic norm strictly bigger than 1. So if I have a rainbow triangle with vertices U, V, W and whose area is A, now we know that the triangle, if I translate this triangle by W, that means I subtract W from each of the coordinates, each of the vertices, then I get these vertices. And we have seen that U minus W will be a red point, V minus W will be a green point, and 0 we know is a blue point. So this is a rainbow triangle. And what is the other thing we know? That when I translate a triangle, the area is unchanged. So this is a rainbow triangle whose one vertex is the origin, and it is rainbow because of this property, which we saw from the lemma. And the area of this triangle is going to satisfy by the theorem 3 prime. We know the two-adic norm is greater than 1. Okay, but the area is same as A itself. So we have proved the theorem 3. Okay, that any rainbow triangle has two-adic norm strictly bigger than, the area has two-adic norm strictly bigger than 1. So let us see now that we wanted to prove theorem 2 because we had seen theorem 2 will imply Monsky's theorem. So our target was theorem 2. So how will we prove that? Now, theorem 2 was saying if we divide the unit square into triangles in any way, in any manner, then there is at least one triangle whose two-adic norm, whose area satisfies this property. Sorry, but now theorem 3 is telling us that any rainbow triangle has this property. So if we show that there is at least one rainbow triangle, then theorem 2 will follow. Okay, so now our focus is to prove theorem 4. So if I divide the square into triangles in any manner, then there has to be at least one rainbow triangle. Okay, so for proving theorem 4, we will have to use a combinatorial lemma. So we have over here, what we have is a triangle, and I have divided this triangle into smaller triangles. Okay, and I have colored the vertices of these triangles using 3 colors. And the shaded triangles are the ones whose vertices have all 3 colors. Okay, that means for the shaded triangle, no 2 vertices have the same color. So we will see a lemma about such a situation. So this is called Sperner's lemma. And the lemma is saying you divide any polygonal region. So in Monsky's theorem, you're interested in a square, and the picture I showed you earlier was for a triangle. But you take any polygonal region, you divide it into triangles, and you color the vertices using 3 colors, C1, C2, C3. Sorry, and then this is the condition that if we know that there are an odd number of C1, C2 edges, that means edges having one vertex is colored C1, another vertex is colored C2. So if such edges, there are an odd number of them on the boundary, then there are an odd number of triangles having all three different colors. So let us just check that in our picture. So suppose we want red green edges. So you see that there is one over here. This is also a red green edge, and this is a third red green edge, and there are no others. So there are an odd number of red green edges on the boundary. So the theorem is saying there should be a triangle which is having all three colors. In fact, there should be an odd number of them. So you see that here we have an odd number of triangles, which we can call rainbow triangles. So but just red green is, you just take any two colors. Suppose I take blue green. So blue green, we have only one edge over here. So again, we have an odd number of blue green edges on the boundary. So again, the theorem says that there will be an odd number of rainbow triangles, which is 3 here. Okay. So same way you can also check if you take blue and red, then you have one edge over here, and that's it, only one edge. So again, an odd number of red blue edges. So but if I had changed this point, if I change this point into a green point, if I color this green, then you see that there are no red blue edges on the boundary. Okay, and then these two triangles will not be rainbow triangles, but this one will still be a rainbow triangle. If I color this green, so it's not necessary that for any pair of colors you have an odd number of edges, but if for one particular pair, if you have, if for some particular pair of colors you have an odd number of edges on the boundary, then that is enough. We can say there are an odd number of rainbow triangles. So let us see a proof of this. So if I take a triangle in the polygon, I call n delta as the number of C1, C2 edges of that triangle. So for example, if I have a rainbow triangle, then there is exactly one C1, C2 edge. And I take S to be the sum of all the n deltas. For all the triangles, I take the number of C1, C2 edges on those triangles. So what is S doing? It is basically counting the number of C1, C2 colored edges with multiplicity. That means if it is occurring as an edge of two triangles, I will count that edge 2 times. So an edge which is in the interior will contribute twice because it will be the edge of two triangles. Okay, so if you look at the picture, suppose I have an edge like this, a red-blue edge. So this is an edge of this triangle as well as of this triangle. So this is a red-blue edge in the interior. We are counting it 2 times. Whereas if I have a red-blue edge on the boundary, I will only count it for this triangle, only count it once. So that's what we are saying, that if I have a red-blue C1, C2 edge in the interior, we will count it twice. And therefore, S will be the number of C1, C2 edges on the boundary, which we count only once. And in the interior, we count them 2 times. Also, we have seen that if I have a rainbow triangle, then the n delta for that is exactly 1. And for all other triangles, either they don't have a C1, C2 edge, or they have 2 of them. So these are the only triangles which have 2 C1, C2 edges. So we will count this 2 times. And for all other triangles, it is 0. In delta is 0. So now what we are assuming that there are an odd number of C1, C2 edges on the boundary of the polygon. So from this first sum, we see that this is an even number and this is an odd number. So S has to be odd. But now from the second expression, we see that this is an even number and S is odd. So this has to be odd. So we see that there have to be an odd number of rainbow triangles. And the smallest odd number is 1. So we can say that there has to be at least one rainbow triangle. Okay, so this is Sperner's lemma. So now let us see how we will use Sperner's lemma. So we wanted to prove theorem 4 that however we subdivide the unit square, okay, in whatever manner we subdivide the unit square into triangles, at least one rainbow triangle is there. So how will Sperner's lemma help us? So this theorem needs some checking, some verifications. So, but they are very easy. So you should try them out. Okay. So we will not discuss all the details for this theorem. So from Sperner's lemma, if I want to say there is a rainbow triangle, then I only have to show that there are an odd number of red-blue edges on the boundary of the unit square. Okay, because then there will be an odd number of rainbow triangles, and so there will be at least one. So, okay, so our aim is to show on the boundary of the unit square there are an odd number of red-blue edges. So a point on the left side cannot be colored red. Okay, you should check this. A point on the top side also cannot be colored blue. And a point on the right side cannot be colored blue also. Okay. So now look at these three. So these three statements, you should check them. Okay, just using the definition of the coloring, how we have. So a point on the left side, the coordinates will be, I will have 0, comma, some a, right? And any such point cannot be red. A point on the top side, its coordinates will be, I have a, comma, 1. Okay, so, and you can show any such point cannot be colored blue. A point on the right side will have coordinates of the form 1, comma, a. And again, such a point you can show cannot be colored blue. Okay, so therefore, what we can conclude that on these three edges, on the left, on the top, and on the right, we cannot have a red-blue edge because one of the colors is missing. So there are no red-blue edges on these three sides. What happens on the lower side? A point on the lower side will have coordinates a, comma, 0. And such a point again, you can show it cannot be colored green in this time. So you should check this statement. So then that means we can have red-blue edges on the lower side. In fact, the origin has blue. It is a blue point, and the point 1, comma, 0 is a red point. Okay. So also, if I have two consecutive blue points or red points, then that will not give us a red-blue edge. So when I'm interested in counting red-blue edges, I can also assume that the red and blue points occur alternately. Okay, so if they occur alternately, so here suppose there are no points in between these two, so that means I just have one red-blue edge. Otherwise, there has to be a red point and a blue point. Otherwise, red and red will be consecutive. So I have a red point and a blue point in between. So I will get 3 red-blue edges. Okay, so you have to think a bit for this, maybe half a minute. Okay, and then you can see that. So there can only be an odd number of red-blue edges on the lower side. So at this point, I will also like to inform you that there is another video on Monsky's theorem. In that, I have explained these calculations in more detail. And if any point you want to clarify, you should look at that video. Okay, there I have explained things in more detail. The point of this video was to give you overview of to give you the idea of the full proof, okay, so that you don't get lost in the details. So do look at that other video if you need any clarification. And so now what we have shown is that on the boundary of the unit square, we only have an odd number of red-blue edges. So by Sperner's lemma, there is at least one rainbow triangle. Okay, so we have proved theorem 4, and that concludes the proof of Monsky's theorem, because we have reduced the proof to proving theorem 4. Okay, but I will make some more comments. So let us just go over the proof of Monsky's theorem. So if you recall, we had made an additional assumption that the vertices of the triangles have rational coordinates. So with this assumption, we had proved Monsky's theorem. So there is a lemma that you can extend the two-adic norm on Q to a norm on real numbers. Okay, and any such norm we will also call a two-adic norm. We will say that a two-adic norm on real numbers means it is a norm on real numbers, okay, which gives the same values as two-adic norm on rational numbers for the rational numbers. Okay, so so we will not prove this lemma. It is a little technical and it uses Zorn's lemma. So we will assume this statement, and this is well known. The result is well known. So we will assume this lemma, and then how will we prove Monsky's theorem? So so this is the statement of Monsky's theorem. Now, in the proof of Monsky's theorem, we had defined a coloring on rational coordinates. That means Q2. So now we will define the coloring on R2 using this two-adic norm on R, using any. Okay, there is no unique extension. You can have uncountably many extensions. So you choose one of them, and any one such, you call it a two-adic norm. Any extension, we will call it a two-adic norm. So you take a two-adic norm on R and you color R2. And now in the proof of theorem 3, so where we were proving that the area of a rainbow triangle has two-adic norm greater than 1. So the same proof will work when you replace the two-adic norm on Q with the two-adic norm on R. So the same proof verbatim will work, and you will be able to show that any rainbow triangle whose vertices now need not have rational coordinates, okay, because we have colored R2. So any rainbow triangle will have a two-adic norm greater than 1. And here the two-adic norm is the norm on real numbers. So that completes the proof of Monsky's theorem, where we don't need this assumption. But let me just give you a quick recap. Okay, what were the main steps of the proof? So this is the theorem, the statement. And so to prove it, we divide the unit square into k triangles, each having area A. Now we define a coloring on R2. So recall our aim is to show k is even. Okay, so to prove that, we define a coloring on R2 using the using some two-adic norm on R, okay, you fix one and define a coloring with red, blue, and green in the same way. Okay, that means by looking at the first maximum of the two-adic norm. Now, then the next step is you want to show that there is a rainbow triangle, right? So for that, you show that there are an odd number of red-blue edges on the boundary of the unit square. And this proof is again verbatim the same as you did it for the two-adic norm on rational numbers. Okay, so once you have this, then by Sperner's lemma, you know that there is at least one of the triangles has to be a rainbow triangle. And now the proof of theorem 3 will tell you that the area of any rainbow triangle has two-adic norm greater than 1. The same proof. Okay, and so we can say that this A has two-adic norm greater than 1. And our aim was to show K is even. So we know that K times A is 1. 1 is the area of the unit square. And taking two-adic norm, we get this. So because two-adic norm of A is greater than 1, so the two-adic norm of K will be less than 1. And that means that K cannot be odd. An odd number will have two-adic norm equal to 1. So K has to be even. Okay. So you see the proof is actually very short, but each of these steps needs some calculations. But so this is the outline of the proof, and with that I will stop this. Okay, so Prof, and thank you for your attention.